Chima, and today I'll be solving Leetcode 509 Fibonacci number. So this is a classic dynamic programming problem that can be solved using a top-down approach, but I'll walk you through the steps to ensure that all nuances and all questions are answered regarding this question. So here it says that the Fibonacci number is commonly denoted as f of n, forms a sequence called the Fibonacci sequence. So it's that each number is the sum of the two preceding ones starting from 0 and 1. That is f of 0 equals 0, f of 1 equals 1, f of n equals, so f at any number within the sequence, so let's say we wanted the fifth number, is going to be the sum of the two previous numbers. So f of n minus 1, so the sum of the fourth number, plus f of n minus 2, the sum of the third number, right? And it's going to be the case for all n values greater than 1, right? So, for example, we want to find the second number of the Fibonacci sequence. So the second number is going to be what? F of 1 and f of 0. And we know that f of 0 equals 0, f of 1 equals 1. So f of 2 is going to equal to 1. If we want to find the fourth number in the sequence, we're going to find f of 3 plus f of 2. And f of 3 is equal to 2, f of 2 is equal to 1, so that'll be 3. Right? So the fourth number of the sequence will be 3. So with that being said, let's see how we can solve this, right? So we know for a fact that if n is less than or equal to 2, we just need to return 1, right? Because the first two numbers are going to be 0 and 1. Oops. If n is, so if n is equal, so if n equals to 0, return 0, right? And if n is less than 2, return 1, right? Less than equal to 2, return 1, right? So because we know if n equals 0 is going to be 0, the first Fibonacci number in the sequence is 0. And we know the second Fibonacci number, f of 1, is 1, as well as the third Fibonacci also being 1, right? So we know that at any point in time, if n, or if we're given an n value that's less than or equal to 2, we return 1. Okay. And if we're given an n value of 0, we return 0. Okay, so now how do we solve this, right? We can just simply just have a recursive call that represents us recursively adding the two previous numbers until we hit one of our base cases here. So what do I mean by this? So why don't we just return fib of fib n minus 2 plus fib n minus 1. Right, so what this does is that it's going to make a recursive call to the second number, or the second previous number, as well as the first previous number. So, or to be more conventional here, let me just do this: fib n minus 1, n minus 2. Right. So the first previous number and then the second previous number. Right, and we're just going to calculate the sum of these two calls until we hit one of the base cases. So let's say we're given f of 4, right? Like we're going to do fib of 4 minus 1, which is 3, and fib of 3 minus 2, which is 1, right? We know n minus 2 is going to give us 1, right? And we know n minus 1 is going to give us 3, right? Which is going to be recursive called again here. So it's going to be 3 and then 2, and 2 is going to return 1. So that's going to be two ones added together to give us 2. So the fib of 3 would actually return 2, right? Because it's going to be 1 plus 1, which is 2. Then I already explained this one, so this would be 2 plus 1, and this should give us the answer here. just have to do self fib, and this runs and it's fine, right? It's working solution. All cases passed, all test cases passed here, but there's a fundamental issue about this solution, right? Right now, this is a purely recursive solution. There's no dynamic programming used in the sense that we're not caching the values of each recursive calls. So when I go to submit this problem, I believe that it shouldn't pass. Oh, it does pass in Leetcode, right? But there is a fundamental problem about this, and that is related to the time complexity, right? Because let me draw this for you real quick. So let's say that we're given n equals, say, 8, right? So with 8, how a recursion works right now, I'm going to get the first number, which is 7. So all these are f of 8, right? So we're going to get f of 7, we get f of 6. And from f of 7, we're going to branch out twice again. We're going to get f of 6, f of 5. From f of 6, we're going to do f of 5 and f of 4. Right? And then from f of 6, we're going to branch out twice again. Give us f of 5, f of 4, branch out here again, f of 4, f of 3, something similar here again. From 4, when we branch out, we get f of 2 and f of 3. Right? Oh, no, I did it that way. F of 3, f of 2. Okay, so we know this is a base case here. Then from f of 3, when we branch out, you get f of 2, f of 1. These are both base cases here. Go from over here to, so from 5, we get f of 4, f of 3. This is a really large tree that I'm drawing here, but just to demonstrate the purpose of using dynamic programming in the top-down approach. So we have 4, 3, then we have 4, we get 3, 2, from 3 we get 2, 1, here we get 2, 1, from 4 we get 3, 2, 3 we get 2, 1, then this repeats again, 3, 2, 2, 1, and I'm not going to draw out the entire tree, but you get the notion of this, right? So these are our base cases here. And you can see if I were to continue to expand this tree, these will also bottom out similarly to these here. And yeah, so as you can see now, like with a number like 8, the tree isn't significantly large, but imagine we're given a very big Fibonacci number, right? You can already picture how large this tree would be, like the amount of recursive calls that we have to make, right? Because every number makes 2 recursive calls, as you can see here. So from 8, we make 2 recursive calls, 1 to 7, 1 to 6. From 7, we make another 2 recursive calls, and from 6, we make another 2 recursive calls, right? So you can see that the number of recursive calls is quite proportional to the height of the tree, or quite proportional to the level of the tree. So for example, on a level 1, we have 1 call. On level 2, we have 2 calls. On level 3, we have 4 calls. Or rather, we say this is level 0, not level 1. So on level 0, we have 1 call. On level 1, we have 2 calls. On level 2, we have 4 calls. So this is level 2, 4 calls. On level 3, how many calls do we have? 1, 2, 2, 4, 6, 8 calls, right? So you can see how quickly the number of calls increase as we go further down the tree, right? So this can be denoted as a 2 to the power n time complexity, because um, at every level, where n equals the height of the tree, because at every level we're basically exponentially increasing the number of calls, right? Because 2 to the power 2 is 4, right? 2 to the power 3 equals 8. And on this level, if I were to expand it out, 2 to the power 4, that should be like 16 or something, if I'm not wrong, if I didn't do the math wrong. So you can see how quickly the number of calls grow, right, per level. And this is where the problem arises due to the exponential nature of this recursive method. So how can we solve this, right? It's important to note here, let me use blue, that we can see that there are many overlapping subproblems or many overlapping subtrees. So for example here, we see that this subtree, 6, is the exact same as the subtree over here, 6, right? It's the exact same tree. We see this 5 is the exact same subtree as if we were to be this 5 over here, right? Same thing with the 3, same thing with the 3 over here, right? So to greatly reduce the time complexity, why don't we say that if we've computed a subtree, we can store it in memory. Like we can store its return value in memory, right? So when we store the return value in memory, we know that we don't have to recompute that subtree again, right? So we know that if we see, like if we compute a 6 when we branch out to the left starting from 8, right? Like whenever we go to branch out to 6 from the right starting from 8, we already know its value, and we won't need to compute any of these values at all. So we won't need to compute 6, we won't need to compute 5, we won't need to compute the subtree of 4, the subtree of 3, etc., right? Because we've stored that in memory, right? And this greatly reduces our time complexity from being exponential to being polynomial, right? So it's going to give us an n squared time complexity, right? And the reason that it's still polynomial is because no, not polynomial. It's going to give us a linear time complexity, right? Because essentially, the way this problem is, the tree that's formed is going to be a balanced tree, right? So we know that we'd only need to compute half of the tree, like whenever we store each of the subtrees like in memory. Like we won't need to compute all these other values, right? So it'll give us a linear time complexity. So that's a huge improvement from going from exponential to linear, just because we use dynamic programming. So how is it going to work? So we're going to store each value in a cache, or in a cache called, DP, which is going to be a hash map or dictionary, depending on which programming language you're using. And based on these values is how we're going to revamp our recursive call. So let's go about doing this. So right now, as I have it, I have my two base cases here. But now I'm going to create an extra data structure here called dp equals, or not dp, let's say cache equals that, right? And as we're doing it here, so we just need to say if n in cache, right? So if we've computed the value before, what do? We return the value in the cache, right? So that's the first step we need to do. Then now we need to change how we're recursively calling this, right? So right now we're just straight up returning that, right? But like, why don't we save this, right? Cache at n equals that, right? And then what do we need to do? We just need to return cache at n. All right, because we're gonna cache the recursive calls, right, into memory, and then if at any point in time while we're making our recursive calls, if the number is in our cache, all we need to do is just return that number that's in memory, right? So we're gonna be able to stop faster than if we were to just have a pure recursive solution. And then at the end, we just need to return the number at n. Let's see how this works now. See, so previously my runtime was 247 milliseconds, beating 36.10 percent of users. Now with this dynamic programming approach, let's see how fast my solution is now. So of course it's Leetcode, so you won't see the huge difference here, but because it's based on how their servers respond, not exactly how fast the solution is. But if in your own time you have in your own time you can go into a code editor and just pass in large values of n, and you'll see the difference. So for example here, that's actually a good point to make here. So for case 4, let's say I pass in a value of 70. Let me close these other cases here, and I run it. Oh, see, yeah, another Leetcode problem here. So it only gives us up to 30, right? Which is going to be fine in terms of Leetcode. But we know that in reality, n can be very large, so we need a dynamic programming approach to help us solve this. So I hope that cleared up any queries.